Okay, so good morning. So today I'm going to do one more lecture on quantifier elimination and results that follow from quantifier elimination. In a sense, this is a bit of a non-standard start to a course on logic, having two lectures on quantifier elimination so early. The reason I'm doing it this way is because these results that we're proving using quantifier elimination, in my view, they're interesting results. And the point is, one can do them at this stage in a logic course, and doing that, in my opinion, helps one to get used to manipulating logical formulas and dealing with the meaning of logical formulas in the structures that we're talking about. So I think it's useful to do this kind of exercise, doing some logic, doing applications of logic, quantifier elimination, before we go on with the main material, the logic course, which we're going to then start from next week. And then from next week, the course is going to follow what you might call the more standard trajectory. That's the path that something takes, the more standard trajectory of a logic course that next week we're going to do the formal reasoning system, a proof system for reasoning with logical formulas. We'll do the soundness and completeness results of that. Then we'll go to model theoretic results that follow from that. So there's an important result called compactness. And after that, we'll go on to the development, which will take a few weeks, that leads to Gödel's incompleteness theorems, kind of one of the main goals of the course. So that's sort of what's to come. But before going into that main trajectory of a logic course, I want to do, as I say, one more week on quantifier elimination. And the point of this is to sort of get familiar with logic and see some interesting results that we can already establish at this stage with the limited technology that we have. We don't really have any technology other than logical formulas and their meaning and structures, and a few normal form results for logical formulas. So to motivate what's coming today, I want to remind you of a result that I already flagged in the first lecture. That's one of the very important results in logic, and is useful in computer algebra. Not exactly the result, but techniques that go into this result are useful in computer algebra. So this is Tarski's theorem. Tarski actually has several theorems, but this is one of Tarski's theorems that I already said it in the first lecture, so I can state it quite briefly now. The theory of the real numbers, if we give the signature of the field operator, well, the ring operations, let's say the real numbers, one can define the multiplicative inverse from this. So this theory over the real numbers is decidable. I wrote down the definition last week of a decidable theory, that there is an algorithm that, given an input sentence, will tell us whether that sentence belongs to, we'll say yes if the sentence belongs to the theory, and no if the sentence does not belong to the theory. So this is a major result. I can, in the first two lectures, I contrasted this with the case of the natural numbers, where it's not the case that the theory is decidable, and that is to do with reasons related to Gödel incompleteness theorems. But for the real numbers, surprisingly, this theory, which is called the theory of real closed fields, so it would be nice to prove this result, and one can do that using quantifier elimination techniques. Actually, it's a bit more advanced than what I want to do in this lecture. This is a possible, I'm going to see how the course goes, but there will probably be a couple of weeks left over at the end of semester after I've covered the main material that will be on the written exam. And maybe covering this result might be a lot. I'll give you some options, but if we do have a couple of weeks left over, I'll give you some options at the end for what goes in the last two lectures. and this might be one of them. So what we're going to do today is what one might call a baby version of this result. And the baby version is we're going to take multiplication out. And we're going to look at the theory over the reals where we have basically just addition. But we'll give ourselves one other feature that gives us more power than just, if we just remove multiplication for this, it's quite limited. So we're going to give ourselves a little bit more expressivity than that. So let me say one of today's main theorems, a main theorem today, is theorem which would be an easy consequence of Tarski's theorem, but we're going to prove it in our own right. So this is the theory of the real numbers with, so we're going to remove multiplication. So we've got the additive group and we've got 1. But in place of multiplication, we're going to put the binary strict order relation in. But this theory is decidable. And this is strictly less powerful than Tarski's theorem, because, as I think I remarked in lecture 1, or anyway, in one of the earlier lectures, the less than relation is easily definable in this signature, because you have x is less than y holds, but you can define that as there exists a z such that x is y plus z times z squared, and x is not equal to y. Maybe use the fact that square numbers are non-negative here. Right, so we're going to prove this theorem, but we'll prove it in such a way that we'll see that this theory is quite interesting in its own right. In fact, we're going to extend the, just like we did last week, we're going to extend the signature a bit to give ourselves more direct expressivity, and we're actually going to work with a slightly extended version of this theory. But the technique again is going to be like last week. We're going to use quantifier elimination. And what I want to emphasize, I think even more this week than I did last week, is that quantifier elimination is not just going to give us decidability. It will give us decidability, but it's going to give us other useful information and non-trivial information about this theory. The quantifier eliminate, so let's call it QE. And QE provides also other useful information. Just write info about the theory. And I'm going to relate that, because time permits at the end, I'm going to relate this information that it provides with a topic of current research in mathematical logic. Yes?
And does that mean then should X and Y be switched?
They certainly should, shouldn't they? Thank you. That would be Y is less than X. Yeah. Thank you very much for that. I've noticed how we needed to use multiplication here. If you don't have the signature without multiplication, less than is not definable, so we have to have it as a primitive if we want to be able to express less than. It's actually an interesting technical question how to prove that less than is not definable, so I'll raise that as something for you to think about. right at this moment, I don't remember what the answer is, but I shall think about it myself too. Right, so as I said, we're going to once again, like last week when we were working with the theory with over an empty signature, we then found it convenient to add some propositional constants, these ones expressing these cardinality constraints, and not just convenient, but in that case necessary to establish quantifier elimination. Actually, in the case of this theory, quantifier elimination is simply true, even if you do not extend the signature. But nonetheless, in order to work with the theory in a mathematically natural way, it's very natural to extend the signature to give ourselves some easy mechanisms for expressivity. So for convenience, rather than in this case necessity, last week it was necessary to extend the signature. So today it's convenient. What we're going to do is extend the signature . So a new signature is going to be, well, we're extending it. So we still want everything that we had before. I mean, I suppose I should have said this is a binary predicate symbol, whereas these are obviously the constants and this is the binary function symbol, but I guess that was obvious. So we have, again, the constant 0 and 1, the plus binary function symbol, the binary predicate symbol strict less than, and what we're going to add is a family of additional unary function symbols, which I'm going to write as Q dot. One, so this is an infinite family. We've got one such operation for every rational number. So where Q dot is a unary, so a single argument function symbol. So before we had this function symbol, our terms were very easy in the sense that the terms were just variables, the constant 0 and 1, and combinations of those formed by the plus operation, which is the only function symbol we had before. Now we've added another unary function symbol, and so the terms get more complicated. So we now have terms such as let's throw it. We now have terms such as a half times, I'm going to use the same one as in my notes, that so notice the notation I'm using. So here I've applied the 1/3 dot function symbol to x, and then I've applied the half dot function symbol to that. I'm adding those two things together using the plus binary function symbol. I'm not saying how I'm bracketing it, but never mind, because we know plus is associative in our model. So notice how we've got a kind of multiplication, but it's only multiplication by a rational on the left. So for each one, it's a rational. So we have terms such as that, but we don't have any way of forming general multiplication such as x times y of two variables. And of course, the meaning of such a term, so Q dot t for a term t represents, well, actually we can just say it like this: the Q dot function symbol is interpreted in the structure, the real numbers, as the function that multiplies the number by the rational q, is interpreted as the function x maps to q times x over the real numbers. And given this interpretation and this kind of, this is like a typical term, and obviously terms can be much, much more complicated than that, but they're all going to look similar. Essentially, the only thing we can do is add together, well, we can add things together. Of course, we might have mixed nested additions and this scalar multiplication, as we might call it. So this isn't as complicated as terms can get, but nonetheless, using elementary algebra, it's very obvious that every term can be put in a normal form. But essentially, we distribute all the multiplications over the additions, and then multiply through the nested multiplications like this. So obviously this will give, this is the same thing as 1/6 times x. We add up all components that we get that have the same variable. So between the pluses, you can only have one variable, and we can put any term in a normal form where for every variable we have one coefficient multiplied, one rational coefficient multiplying it. So q2 times x2. So any term is going to have some number of variables. Each one can just be one rational scalar multiplication of it, and then the remaining terms that are rational multiples of one, just simply. So this isn't even an official term over our signature, but over our signature we don't have a single rational here. This would mean q times 1 if you want, but I'm just going to write it like this for convenience. So hopefully you can see that however complicated you make terms over this signature, you can always prove, I mean, it's always the case that any term is equivalent to one in this formal form. So that's going to be quite convenient for us. Okay, so what we're going to be interested in is the theory of this signature over the real numbers. So that obviously extends this theory. You're adding the rational, we're adding these scalar multiplication by a rational, this operation. And that's the main theory we're going to look at. That sorry. So this is today's main theory. So let's give it a name. So the theory is the theory over the real numbers of the signature.
It should be a plus instead of the.
It should indeed be a plus instead of times. Thank you. So it's very standard theory, this, but it doesn't really have an agreed name. People sometimes call it linear arithmetic, but then you have to be careful because there's linear arithmetic over the reals and linear arithmetic over the natural numbers. So I'm going to call it the theory of rational linear expressions. So I think that's self-evident why that's appropriate. So rational, so I'm going to call it RLE. And we're going to prove theorem that RLE enjoys quantifier elimination. But maybe now, in case I need to refer back to it, this can be theorem A. Okay, but before doing this, I want to do two things. So firstly, I want to relate this theory of rational linear expressions to the theory I started with, the one that does not have the additional function symbols for scalar multiplication by rational. And secondly, in order to prove this, I want to refine a little bit our criterion for establishing quantifier elimination. So we had this criterion last week that a theory enjoys quantifier elimination if and only if every existential formula quantifiers are eliminable from every formula that's an existential quantifier over a conjunction. We're going to have a slightly improved version of that result, which will be useful for application in this case. So the first thing I want to do is explain how this theory that we've added the new function symbol, the scalar multiplication, how this relates to the theory without the scalar multiplication. So I'm going to show that it's basically the same, in the sense that scalar multiplication is already definable in the first theory, just we don't have a primitive notation for it, but we can nonetheless define it. Scalar multiplication by a rational. So let's clear the board. So what we're establishing, the main fact here I want to establish is that actually, well, this theory, I might as well use its name, rational linear expressions, is no more expressive, even though it's got a larger signature, than the original theory we had without multiplication. So then the theory of the reals is addition, one, and left-hand relation. So to establish this, we show that these new function symbols, the rational scalar multiplication, every few times function is definable in the theory again. Well, I wish I'd given this a name, but anyway, I haven't. So last week, in order to motivate adding the new propositional constants that were expressing the cardinality constraints to the empty signature, and showing that that's really more expressive than sentences, than formulas over the empty signature, I introduced the general machinery for defining predicate symbols in a theory, saying when a predicate symbol is definable in a theory, and then extending a given theory with a new symbol for a relation that's definable. So we did that last week for predicate symbol, definable relations, and extending a signature with predicate symbols that express definable relations. Here we're in a slightly different situation because we're not extending with a predicate symbol, we're extending with new function symbols. So we want a corresponding theory of definable functions in a theory. And when a function is definable in a theory, we can extend the signature with primitive function symbols for the definable functions. So we need a theory. We look at the notion of definable function in a theory. And the point here in the example is that in this theory, without the rational scalar multiplications, the rational scalar multiplication functions are going to be definable. So there's an easy part to this and a difficult part. The difficult part is actually much more difficult than one would expect it to be. So the easy part is, what does it mean for a function to be definable? So the most general way of defining a function, say a function that takes n arguments, is by using a formula that has n plus 1 free variables, and requiring that the relation expressed by that formula expresses the functional relation that relates the n x variables, say, to the result of applying the function to them. So we say that a formula A that has, let me just see if I use n here or k. Yeah, I use n. I mean, obviously it doesn't matter. I just don't want to get myself into problems that because my notes say something different, I'm writing something inconsistent on the board. So the point is, we want to say when this expresses a functional relation, y is functionally determined from the variables x1 through to xn, and I guess most of you know when this is the case. So we say that this, what terminology do I use? Defines an n-ary function. N-ary function relative to a theory T. So whether or not a particular formula defines a function might depend on the theory we're looking at. So if, and here it's not surprising at all. What does it mean for a formula to define a function? Well, a relation is functional if all x1 through to xn, there exists a unique y that satisfies the relation. And exists a unique we can express easily using first order logic, and an easy way of doing it is to just separate out the existence statement and the uniqueness statement. So the existence statement is that for all x1 through to xn, there exists a y such that A holds, so A x1, xn, y. Remember, again, this notation is saying that A contain all the free variables in A belong to these variables that I've mentioned. So that's that the existence holds, and secondly, the uniqueness property holds. Well, again, we can say that easily by we say for all x1 through to xn, and for all potential y and y prime, if y and y prime are both in the relation to x1 through to xn, then y equals y prime. Okay, so that's what it means for a formula to express a relation relative to a theory T. And sorry, not relative, to define a function relative to a theory T. And the point is, whenever a theory defines a function, whenever a formula defines a function, we can, without changing the expressivity of the language, we can add a function symbol for that function to the language. So if A defines a function as above, then we can extend signature with a new n-ary function symbol f. I'm going to just write f superscript new. And at the same time, we extend the theory T by adding, just as in the case when we added more predicate symbols expressing an n-ary relation, we extended the theory with equivalences, in that case, saying this predicate symbol indeed defines the intended relation. We want to do the same thing. We want to do the same thing with the new function symbol. We want to add a sentence to the theory that tells us this function symbol indeed is a function symbol expressing the function defined by the relation A. So we extend the signature with a new function symbol, and we extend T by adding a new sentence to it and then closing under logical consequence so standard notation for this is we say we keep the theory T and we add to it also the logical consequences of the new equivalence that we're adding. And the new equivalence says for all x1 to xn, all you need to say is that the relation A holds of x1 through to xn together with the term that we now have in our new signature, f new applied to x1 through to xn. That's all you need to say, because we're assuming that the relation A is already known to be functional, and that that's all the information we need to give to say that f new is expressing that function, is that indeed f new satisfies the relation with respect to x1 through to xn. So the point is, so what we refer to this as so the point is, this is extending a signature with a definable function symbol. And in fact, let me put this on a new board. And the main result about this is that it does not change expressivity of the theory. We cannot say anything new in the theory with the extended signature that we could not say before in the theory that in the original theory T that we started with, and the original language that we started with. So, extending a theory with a definable function symbol.
Sorry to interrupt. Could you just turn the camera,
or any
please?
number of definable function does not increase expressivity. And how's that expressed? Well, there's going to be a mathematical result that tells us that this is true. So this could be a theorem. In my notes, I called it a proposition. There's actually, in the rough notes for today, which is what I'm following at the moment, I actually missed something out here that I don't think I'm going to edit in, but I shall put it in. I shall put it in on the board here. So this proposition is going to say there is no increase in expressivity. So let's make two statements. The first one is the one that's missed out. But so the original theory is T. So let's have original theory T. New theory T prime. So T prime is T plus this statement that statement F is. Oh, I did, didn't I? Thank you very much. So the first one says that the new theory T prime is what's called a conservative extension of the original theory, meaning that any formula in the original language is true or valid in the extended theory if and only if it's valid in the original theory. So for any formula B in the original signature, we have T prime B holds in T if and only if B holds in T prime. So this says T prime is a conservative extension of T. So the extension is the left to right implication. T prime proves all the stuff that T proved, but it's conservative in that it doesn't, within the language that we had before, T prime doesn't prove anything new. More interesting statement is the next one, which tells us that we've got equivalent expressivity. So this is for any B in variables, let's say Z1 through to ZK, in, or let's say C, in the extended signature, there exists a corresponding formula in the original signature with the same variables in the original signature, such that S dot P C, so for all Z1 through to ZK, B holds if and only if C. So which theory do I need to put here? Just to check that we're ending the first hour, so just to check that somebody's still awake. Sorry?
The new one.
The new one, thank you. It has to be the new one because we've got a formula C here that's from the new signature. So it wouldn't even make sense to have T back. So this is the whole proposition. It's quite cumbersome. So basically, the idea is straightforward. We've got a definable function. And we don't want to cumbersomely, we might have some complicated formula expressing it. We don't want to, in a cumbersome way, always use that complicated formula. But also it's a function, so we want to be able to kind of put it into terms rather than always have to put quantifiers in to get hold of the value. So in order to allow us to put it into terms, we add a new function symbol. And this is just what we need to say, well, actually adding a new function symbol, we haven't changed what we can prove in the original language. And actually, we also haven't changed what we express, because anything we can express now in C is equivalent to something in the original language. So now we come to the surprising part. The surprising part is that proving this is actually quite a nightmare. And I don't even know, I mean, I haven't looked very thoroughly, but most logic texts gloss over this. If you actually want to prove this rigorously, it's really quite complicated. So actually, I'm going to gloss over it as well, because I don't really know a very nice way of doing it. You're going to do examples of this in the exercise class, and that you, in doing those examples, you will see that there's kind of an algorithm there, but you will begin to realize that it's not going to be very straightforward. So to make the algorithm explicit. So if anyone of you feels interested to try and find a really neat way of proving this, or to have a good look in the literature and find some nice reference that does it in a neat way, I would be very, very happy to learn of that. But before that happens, we're just going to accept it and kind of gloss over it. But you will, as I say, you'll do examples in the exercise class. So it's almost break time. I'm going to very, very slightly overrun, because having got, we've had the 15-minute break. But having got to this point, it's natural to finish it, because what I want to show you, and this is now not difficult, I want to show you that these scalar multiplication operations are definable. These unary function symbols are definable in the theory of the reals with just plus, 0, 1, plus, and the less than relation. So let's use black here. So I want to show that Q dot is definable. And this is really not hard. So we've got the general machinery that works for arbitrary function symbol, arbitrary functions of arbitrarity, of taking n arguments. Here we've just got a unary function, and actually it's not difficult to show it's definable. So anyway, let's do it. So this function is definable in the theory of the reals with 0, 1, plus and less than. Well, it's really easy. We want to find a defining formula. Let's say AQ in two variables x and y, which is expressing the relation that y is q times x. And that's really straightforward. So in the case that q is greater than 0, then such a formula could even leave it as an exercise but anyway, it's so easy, let's not do that. But you simply say some number of multiples of x is some number of multiples of y. So if q is m over, let's see which way I've got it in my notes, is m over n. So it's a rational, so we can always express it as a fraction. And then q times, saying y is q times x, it's the same thing as saying m. If we add x to itself m times, that's the same as adding y to itself n times. And if q is minus m over n, well, it's minus m over n, which is less than 0, then we simply just put the y's on the other side. So we just need to say x added to itself n times plus y added to itself n times equals 0. And if q equals 0, well, then the relation is simply y equals 0. Doesn't mention x, but it doesn't have to. It has to just have no free variables other than x and y. Okay, so well, it's only by my watch 2 minutes past 3, so not 3, 9. So we start again at 17 minutes past 9. Okay, just pause the recording. Two things before proving theorem A, this decidability theorem, or the theory of rational linear expressions. The first one was how to extend a theory with definable function symbols. So we've done that. The second one is to refine the criterion that we had last week for establishing quantifier elimination. So we had last week that a theory enjoys quantifier elimination if and only if quantifiers are eliminable from formulas of It's almost a bit of overkill for the application, which is this particular theory of rational linear expressions. But it's also not standard in the literature, what follows. So the terminology I'm going to introduce is my terminology, but it seems it's not going to take us long, and it seems to me the natural way to do it. So let's do it. Let me get this out of the way. So I'm going to introduce the notion of what I call, I don't think anybody else considers, a literal base. So for a theory T, we say that a set of literals set, let's call it L, curly L. That's a curly L because I'm using a standard L for an individual literal. So a set L of literals is a literal base if every literal is equivalent in T as every literal that exists, not just the ones in L, is equivalent in T, theory T, to a formula built from literals in L, in the literal base, literals in curly L, using only conjunction and disjunction. So in particular, what you're not allowed to use is negation. So for example, in the theory we're dealing with, our theory of rational literal expressions, then collection of all literals perform either T1 is less than T2 or T1 equals T2 is a literal base. So in other words, we've only got two relation symbols. We've got equality and strict less than. But we've got four, using those two relation symbols, we've got four different ways of forming literals. We've got less, strict less than, not less than, the negation of both, equality and the negation of equality. But in fact, one doesn't need the not less than and the negation of equality, because they can be expressed using conjunctions and disjunctions of literals of this form. And the reason for this is because has a U in. So we need to be able to express a negation of a strict less than. Well, it's a negation of a strict less than as disjunction, as combination of disjunctions and conjunctions involving just literals. This form, well, in the real numbers, if T1 is not less than T2, that's the same, not strictly less than T2, that's the same thing as T2 is less than or equal to T1. So this is equivalent to T2 is less than or equal to T1. In other words, T2 is less than T1 or T2 equals T1. And not equality, T1 is not equals to T2. Well, that's equivalent in the real numbers. If T1 is not equals to T2, well, it's a linear order. So in that case, either T1 is strictly less than T2 or T2 is strictly less than T1. This is equivalent. So to T1 is less than T2 or T2 is less than T1. And I'm just going to state two propositions about literal bases. That the first one is that we have nice normal form results with respect to literal bases. So we had all these normal form results like conjunction, like negation normal form, conjunctive and disjunctive normal forms, in which case we were always saying a formula is equivalent to some combination of conjunctions and disjunctions in some appropriate form with literals at the end. All negations are in literals. Now what we can do is say, rather than having negations in literals, at the end of this, inside the formula, we only have literals from our literal base. So the first statement is the normal form result. So let's see how I write it in my notes. That's probably easier than coming up with a good formulation on the fly. So if L, purely L is a literal base, then every quantifier-free formula has equivalent formulas so there's going to be a negation normal form version, a conjunctive normal form version, and a disjunctive normal form version. And indeed, these are going to be in respective normal forms. In negation, conjunctive, oops, that's it. Bloody J, conjunctive or disjunctive normal form respectively. All of whose literals are taken from the set L. All of whose literals are from the literal base. And the proof is just the usual proof of negation normal form, conjunctive normal form, disjunctive normal form. Well, or rather, you go into negation normal form, you then simply replace your literals like this, and you're still in negation normal form. So you're done for negation normal form. And after that, if you want conjunctive normal form or disjunctive normal form, you apply the algorithm that gives you conjunctive normal form and disjunctive normal form, and it never changes the literals. So anyway, so it's easy. I'm not going to prove it, but I'm just going to leave it as a statement. But the more important to our purposes, although this is relevant to the proof of the next result, the more important to our purpose is the next proposition, which refines the criterion we have for establishing that a theory has quantifier elimination. So a theory T with literal base L, where the L enjoys quantifier elimination. So I'll just say quantifier quant.elim dot. If and only if quantifiers, so I'll just write quant dot, are eliminable from every formula of the form. So we just consider exactly the same form that we had before. So single existential quantifier followed by conjunction of literals, but where we make the obvious modification that we only need to consider such formulas in cases in which all these literals come from the literal base. Okay, so where, well, as before, each literal contains the variable x, and the new condition, and each literal belongs to the literal base curly L. So I hope you can distinguish between my curly L and my not curly L. So let me underline that, because that's the only new condition that we have for this result. And the proof is once again the same as before. So it's exactly the same as last week's proof. The only thing is, in last week's proof, at various points we had to put formula in conjunctive or actually disjunctive normal form. And when you put the formula in disjunctive normal form, you need this result at that time. So this result is used to prove this result, and this result, so basically again, same proof as last week, modulo being careful about the literals. Now that we've got this result, we're going to use the fact. So we're now in a position to go and prove theorem A, that the theory of rational linear expressions has quantifier elimination. We're going to use this proposition here, and we're going to use the fact that this is a literal, this particular collection I gave you here, this particular choice of literals is a literal base for rational theory of rational linear expressions. So we're right now in a position to go and prove theorem A. Well, sorry, no. Wait, was theorem A decidability or quantifier elimination? I don't actually remember what I.
The second one was theorem
Sorry?
A. The second one was theorem A.
Yes, but did I say that the theory of rational linear expressions is decidable, or did I say it has quantifier elimination? Okay, good. Well, in that case, we can prove theorem A. I didn't actually call it theorem A in my notes, so that's why I was asking you. Anyway, let's. And this is actually easier than the proof we did last week. So, proof of theorem A. Namely, that the theory of rational linear expressions enjoys QE by elimination. Okay, so by the proposition, we just need to prove that every formula, let me call this again star. Every formula of the form star enjoys quantifier. So the quantifiers are eliminable from every formula of the form star. So by the proposition, we just show quantifiers are eliminable from every formula exists X, L1 and LK star, where X, where each Li contains X, and is from our literal base, so and is either, so our literal base consisted of only atomic formulas, so only positive literals involving a strict less than or an equality. So it's either T1 is less than T2 or T1 equals T2 for some terms T1 and T2. Okay, so now we're going to use the normal form for these terms T1 and T2. So each of these terms here, Ti, they don't all contain the variable x. It's not true that every term needs to contain the variable x. Just when we have two terms on either side of a relation, one of those terms needs to contain the variable x. But our terms in general will contain variables including x and possibly, what do I call them here? And possibly x1 up to xn, some other three variables. And as I had remarked earlier, every term can be put in normal form. So in this case, let's use the same notation. So we're going to have a normal form will be some rational multiplication of x plus some family of rational multiplications of x1 to xn. So I'm going to number the rational multipliers in the natural way, followed by plus potentially some constant, some rational multiplication of 1 at the end. So we've got formulas in which we can put the left-hand side in a normal form like this. So a linear expression in variables x1 through to xn. And we can put the right-hand side in a similar normal form, so another linear expression in the variables x1 through to xn. We can now do simple algebra, moving the variables onto one side. And we're going to do that in such a way that we leave x on one side and put all the other variables on the other side. So using algebra, each literal that we have in our conjunction star, so each Li is equivalent to a literal in one of the following forms. So actually, we can put x on one side and we can multiply through by its rational coefficient. So it's on, so that we just isolate x itself. So we can actually put, we can always get it either x equals t or x is less than t or t is less than x. So where x does not appear in t. So this is just basic algebra, but I apologize if this is too trivial for you, but just to clarify what's going on, I'm going to give an example, and it's better to have an example than to painstakingly explain exactly why this is always the case, but the example will be illustrative. So we're starting off with some relation between two normal forms. So e.g., if we have a relation between two normal forms, I'm going to use the same example as in my notes. So if we've got something like a third times y plus minus a fifth times x is less than a quarter times x plus a half times z plus 2. We can replace that by, because it's equivalent to, can be replaced by, well, we just put the x's on one side, all the other variables on the other side, and then multiply through by the reciprocal of the coefficient of the rational coefficient of x. And in this case, we get, and I hope I did the calculation correctly when I wrote the notes. So we get 22 over 27 times y minus, which is of course plus, and then a minus rational factor, but a minus rational multiple, but sorry, that's a 9. So minus 10 ninths z minus 40 over 9. Oops, keep on writing q instead of 9 is strictly less than x. Okay. So basic algebra from school, from high school, or even earlier. Okay, so
There should probably be 10 divided by 18 before z.
really? Well, anyway, so you can think about that. If I've made a mistake in the algebra, it doesn't.
No, yeah,
Yes.
sure.
I don't want to think it through. I mean, you know, there's such things are for young children to do. I've had enough pain trying to read through my daughter's attempts at doing mathematics at school, so they find it much easier than I do. Oops, that's the wrong button. So what we do is we've got the star that we want to eliminate the quantifiers from. We replace every literal in star. Star with one of this form. So actually in my notes, and let's keep that, I call it star star. With one of the form star star. Form star star. And we need to eliminate quantifier, the existential quantifier from the resulting formula. We need to eliminate exist x from the resulting formula. Okay, so we now do a case split like we did last week. There are two cases. So the first one is that one of the literals is an equality. So that we can again say without loss of generalities, is the first literal is an equality. So such an equality is x equals t, where t contains only variables different from x. Only variables different from x. But then, just like last week, the equivalent quantifier-free formula is we simply take the literal L1 out, and in the other literals, we substitute the term t, which no longer contains x, for the variables x occurring in them. So the equivalent, so this was just the word, equivalent quantifier-free formula so this is exactly the same thing we did last week. We take the remaining, the conjunction of the remaining literals, L2 up to LK, and we substitute term t for the variable x. The only difference from last week is that now we have last week we only had variables around, this week we've got interesting terms because we've got constants and function symbols to build the terms as well as variables. So we now come, like last week, the main case is the other case when we don't have any equalities. And again, I'm going to see if, so last week it was very complicated, that case, and so I left it as a sort of challenge for the break to think it through. This week it's much easier, and indeed it's easier just even if you haven't seen it before, and you may have seen something similar before, in which case it should be even easier still. So otherwise, if there are no equalities, then we need to eliminate the quantifier with this x from, and the formula is of the following form now. So we don't have equalities, so every literal is one of these two inequalities, either x is less than t for some term t not containing x, or t is less than x for some term t not containing x. So you can simply write that as a conjunction. Let's put the ones in which, let's use little s's for the terms not containing x that occur on the left-hand side of an inequality. So we've got the conjunction of inequalities S1 is less than x and Sm is less than x. And on the other side, we've got x is less than t1 and x is less than tk. We need to find an x greater than all the Sm and less than all the t's. We want to form a quantifier-free formula which is equivalent to the existence of such an x. So, okay. So now, can somebody suggest the answer here? What's the quantifier-free formula that's equivalent to this?
Maximum of is smaller than minimum less.
Well, so you might want to say the maximum of t is smaller than the minimum of x, but how can we express that without quantifiers? We don't have an operation for maximum or minimum in our signature.
Every s is smaller than every t. Yeah.
Right, so that's what we need. So we don't have, we can express maximum using quantifiers, but it's not easy to express it without quantifiers. But actually, what you can do instead is, if pairwise every single s is strictly less than every t, then that's equivalent. There exists an x by the density of the real numbers. There exists an x if and only if that condition holds. So the equivalent quantifier-free formula is conjunction over from I 1 to m, and the conjunction from j is 1 to n of si less than tj. The reason I was suggesting you might have seen something before is, I think in the exercise class last week, you proved the quantifier elimination for the theory of dense linear orders. But this is basically the same argument. The only difference here is that we now have, the reals are a dense linear order. The only difference now is we have some interesting term structure around. But we use the algebra associated with the term structure exactly to get things in the form, precisely so that we could use this stuff, this step, the same as before. So we're done. So having done that, I'll now prove decidability of the theory of rational linear expressions, and then we'll have the break. And then I think the next part is going to be a shorter hour. And then the next part I want to talk about consequences. So other consequences other than decidability that follows from quantifier elimination. So while I'm clearing the board, this is 2 weeks in a row now that we've established quantifier elimination of theories, and that we then go on to use quantifier elimination to prove decidability. It's not the case in general that having quantifier elimination means that a theory is decidable. So what quantifier elimination gives us is it gives us just some fact about the theory. You don't need quantifiers to express first order properties in the theory. In some cases, when you prove the existence of quantification in such a way that we're doing explicitly here, involving basically an algorithm for constructing the quantifier-free formula, then you get an algorithm. Well, so then you have an algorithm for converting any formula to one in quantifier-free form. Even that may not give you decidability, because it may not be decidable if a formula without quantifiers belongs to the theory or not. But to get decidability, you need, from quantifier elimination, you need an algorithm that gets the formula into quantifier-free form, which we have in this case. It was clearly algorithmic, what I was doing. And in addition, you need an algorithm for being able to decide whether a quantifier-free sentence belongs to the theory. So we shall see that we have that in this case, and it's actually very straightforward. So this is a corollary of what we've done. So the theory of rational linear expressions is decidable. And hence, the original theory of the reals with 0 plus 1 and less than is also decidable. Because if we have an algorithm for the theory of rational linear expressions, we want to decide the theory over the reals, or we simply take a formula over the theory in the original signature, we simply take a sentence in the original signature, it's still a sentence in the extended signature, we apply our algorithm to it, and by that conservativity result, the answer to that algorithm will be correct for the original theory, because this was a conservative extension of the original theory. Right, so proof. So given an input sentence A, our algorithm proceeds as follows. So firstly, we find a quantifier-free sentence B equivalent to A. So find a quantifier-free B equivalent to A using the algorithm implicit in quantifier elimination. implicit in the proof of quantifier elimination. So all this putting stuff in normal forms and then doing the steps on the board there in quantifier elimination. So we end up with a Boolean combination of literals that have no variables because this was a sentence. So we end up with a Boolean combination literals with no variables. So every such literal has a normal form. Well, the literal is going to be some term involving only no variables, so only 0 and 1 and rational multiplication and addition is less than or equal or something to another term of the same things. But if you put any one of those in normal forms, these linear expressions, there are no variables there, so each term is just simply a rational number. So for the normal form, the possible normal forms are Q1 equals Q2 for two rational numbers, Q1 is not equal to Q2, Q1 is less than Q2, or Q1 is not less than Q2. Where in each case you've got fixed rational numbers on either side. And these relations are simply decidable between rational numbers. So since such relations are decidable, given 2/3 and a half, I can decide that 2/3 is not less than a half. There's an algorithm that will return no, 2/3 is not less than a half. It's very easy. So since such relations are decidable, we replace each literal by true or false as appropriate. Okay, so we now have a Boolean combination of true and false, and just so using ands and ors, and just using truth tables, that every such combination calculates to either true or false. So we're using truth tables, calculate the resulting Boolean combination of truth values, That will be either true or false. And we wanted an algorithm that returns yes if the sentence is in the theory, and no if not. So the algorithm returns yes if we've got true with the result, and no if we've got false with the result. And we don't. The one remark about this is, compared with last week, so last week when we had the theory of what I was saying, finite cardinal bounds, and in the end when we came to eliminate the quantifiers from a sentence, we were left with some Boolean expression involving these cardinality constraints. And it was not necessarily the case that any such expression would be true or false. It depends on the size of the structure in which we interpret it. Here, what we're dealing with is the theory of a single structure to begin with. So as we saw in the second lecture, the theory of a single structure is always complete. So in this case, for every sentence, it's either true that the sentence is in the theory or its negation is in the theory. In other words, every sentence is either true or false. And so now our algorithm is actually calculating, is the sentence true? So given an input sentence, is it true in the reals or is it false in the reals? So we always get the truth value at the end. We're essentially calculating the truth value of the sentence in the reals. Okay, well, it's 3 minutes to 10, but that's a good stopping point. So I'm going to pause the recording. Okay, so in the last part today, what I want to tell you about is we've got this quantifier elimination result for the theory of rational linear expressions. And I want to show that we've had one consequence of that. We've shown decidability, which is a nice result. But I want to show that quantifier elimination results have other kinds of consequences too, some of which are perhaps even a bit more interesting than decidability results. Although decidability is very important. For example, this decidability that I showed you, kind of ideas in that really go into computer algebra packages. So there is software in the world that uses the kind of ideas that are needed in this that arise from this decidability result in order to be able to automatically reason with linear constraints about real numbers, for example. I mean, even so, one would never use this as an algorithm, but as a consequence of the decidability and quantifier elimination for rational linear expressions, one can get from that, you can think about it, an algorithm, an inefficient algorithm, even for linear programming, if you know, for those of you who know about linear programming. But anyway, I'm going to look more on the logical side and talk about, so essentially, the remainder of the lecture is going to be corollaries of quantifier elimination for this theory of rational linear expressions. So the first one is more or less just a remark, but as I already commented at some point in the lecture, when we introduced this theory of rational linear expressions, we were introducing these new function symbols, so this rational scalar multiplications. I said it's not actually necessary to do that, whereas last week it was really necessary to have the propositional constants that express the cardinality constraints. This week it was just purely for convenience that we added these rational linear functions. And the reason for that is that the original theory we started with, the theory of the reals, with plus, not times, but 1 and less than, this theory itself enjoys quantifier elimination. It enjoys quantifier elimination. Proof of this is that you simply observe, so we want to eliminate quantifiers from this theory. Well, we eliminate quantifiers using the theory of rational linear expressions, and then we get a quantifier-free formula using rational linear expressions. So we get a formula with literals for rational linear expressions. You simply observe that every literal over the signature 0 plus 1 less than, and these scalar rational multiple operations is equivalent over R to, and in fact, one can again get away with a single literal. You don't need even to use conjunction or disjunction, to a literal over just the original signature where we don't have the scalar multiplications. So The proof of this is a bit like defining the scalar multiplications using the original signature. Only, it's a little bit more involved, but actually not very much involved. I don't want to go into the detail, but I'll leave this as it's a little fun thing, not that fun, but anyway. It's well, anyway, if you're ever bored and stuck to something to do, then you could think about that. Maybe realize that you weren't actually bored afterwards. Anyway, that's the first. No, but anyway, so a little puzzle. So that's the first consequence of quantifier elimination. I want to do 3. The second one, this is the most interesting one from a mathematical perspective. And in order to state it, I want to do a little bit of preliminary work. So the decidability proof we did, we applied quantifier elimination to a sentence to see if it belonged to the theory, and we saw that any sentence we could reduce it to a Boolean combination of truth values, and it calculates to a truth value. So quantifier elimination for sentences is kind of, well, it gives us an algorithm. It's interesting from that point of view, but in terms of what sentences can express, it's boring because sentences can just express true and false. It's interesting to see what quantifier elimination tells us about what an arbitrary formula with 3 variables can express. Because it says that however much we use quantifiers in a first order formula, in the end, we can get rid of them here and we've got some sort of complicated, but nonetheless quantifier-free formula involving 3 variables. So the main question for the second corollary is the following. So question, what does quantifier elimination tell us about the expressivity of formulas with 3 variables? So formulas without 3 variables, namely sentences, they're all true or false. So they don't really have any interesting expressivity in that sense. But formulas with 3 variables do have interesting expressivity. So I'm going to consider a particular way of interpreting formulas in 3 variables, which has mathematically turned out to be very, very profitable. So let's consider an example formula, e.g. formula, and I'm going to just have a quantifier-free formula just to make things easy, but we're going to use similar considerations for any formula. So I'm going to just, it's a bit arbitrary, but this is the one in the notes. So the formula x is less than z1, or -1 is less than x, and x is less than z2. So that's the sort of thing we can express with 3 variables. But why 3 variables become interesting is because, what we can do with 3 variables is we can instantiate, we're interested in interpreting formulas over the real numbers, and we can instantiate 3 variables with any real number and have a look at what we're defining in that way. We don't need to restrict ourselves to real numbers that are definable in our theory, which in this case would be just the rational numbers. And what we're going to do is we're going to look at the formula of what we obtain if we instantiate all 3 variables except 1 in a formula with real numbers. So that's why I'm naming the variables in this way. I'm going to have formulas containing a distinguished variable x and other variables which I'm going to use z1 up to zk for. And I'm going to instantiate those z variables with real numbers. So we can consider the real numbers, we instantiate them with parameters. And so for real parameters, parameters, so let's call them A1 and A2. So these are actual real numbers. We consider the above formula as expressing a set. So it's namely defining the set of X that satisfy this formula if Z1 is interpreted as A1 and Z2 is interpreted as A2. So it's expressing basically a set of real numbers such that X is less than A1 or -1 is less than X and X is less than A2. Okay, so we're defining, so this formula defines in parameters this particular set. So for example, if A1 is minus E, where E is Euler's number, that's certainly not definable in theory, but it's a perfectly legitimate real number, and A2 is pi. So I wanted to work pi into the lecture today because, as you may know, today is Pi Day, and there's going to be the competition for reciting digits of pi at lunchtime. At least I think it's at lunchtime today. So, I mean, you know, you've all been around for some time, well, not all of you. In fact, for those of you who are here on Erasmus or visiting in one means or another, you may not know about this. But anyway, this is an exciting thing that happens every month, the 14th here. So go outside at the appropriate time, which I'm not sure what it is, but anyway, then there will be a competition reciting the digits of pi. Anyway, for our purposes today, pi is a real number, and this formula here defines the set. In this case, we get the set. By the way, there's a mistake in my notes that are going to be online here where I've got an and there. But anyway, that shouldn't matter. So in this case, we get the set of real numbers from -infinity to -e, the open interval there, and together with another open interval, that's a sort of half open interval, if you like, extended to the, well, anyway, it's open, and then -1 pi on the other side. So we say, and it's a long time since we had a single star, so let's use a single star. So this shows, so we say that star is definable in parameters in the theory of rational linear expressions. So here we're using the parameters. So here we're using -c and pi as parameters. So this was a simple case. I mean, it was a simple quantifier-free formula, but it's turned out to be very, very useful mathematically to consider the question, what sets can we define in parameters using an arbitrary first-order formula? And as a consequence, a not very hard consequence of quantifier elimination, we get an answer to that. Or maybe I should give the definition of definable in parameters. So we say a set of real numbers is definable in parameters we may need to say which parameter, we might sometimes want to say which parameters we're defining things in, so let's call them A1 to AN in part of the N. By a formula, so it's an arbitrary formula, may have quantifiers with the variable X, which is the variable that's standing for the reals in the set, and variable Z1 to Zn, which are the variables that's going to be instantiated with the parameters. So if X is the set of real numbers R such that A holds for R for X and A1 for AN for Z1 to Zn. So here I'm writing this to mean A holds under the environment that assigns little x, the variable little x to R, and the variables A1, AN to AN, A1, AN to Zn. So maybe just going to often use this notation. This means we like the R, A holds in R under the environment that maps X, Z1, Zn to R, A1, AN. So this is the environment row up at the top. But this notation is easier to read, so we use that. And I didn't move the camera. So let's move the camera while I'm clearing the other board. I don't quite know what's happening. I mean, there are like 6 people on Zoom, but either it's impossible for them to, because they've got the speaker here, and you know, it'd be useful if sometimes I didn't move the camera, that somebody could shout. But perhaps something in the technology is not working. I just don't know. Anyway. So the theorem, which is an easy consequence of quantifier elimination in our case, is that a set X is definable in parameters using a formula in the theory of rational linear expressions. Definable in parameters by a formula AX. So that's X, Z1 up to Zn by some formula. If and only if X is a finite union of intervals. Not necessarily open intervals. It might be half open, half closed, or closed, or open, and the intervals might go off to infinity in one direction, as they did in this example. And it's kind of obvious that every finite union of intervals is definable in parameters. You simply make a disjunction of formulas involving conjunctions of less than relations, or potentially with an equals as well. So just like, well, just the formula that we started with gave us this example. The interesting thing is the other direction, that there are no more complicated sets definable in parameters. So no matter how complicated we make a first order formula, and no matter what parameters we consider, still the set definable from it is a finite union of intervals. Again, I don't want to give a fully detailed proof, but the proof is rather straightforward. So proof is eliminate. Well, one direction is easy, but if you've got a finite union of intervals, then we're definable in parameters. So this is easy. And the other direction is we apply quantifier elimination to A. And then rewrite the formula in disjunctive normal form. Then rewrite the quantifier free formula, the Q dot F formula in disjunctive normal form. The reason for that. And once again, I'm going to leave it as an exercise to fill in the details.
So a single point counts as an interval.
So a single point counts as an interval. So very good point there. So actually, given that you've raised that, maybe I should actually tell you what an interval is. So recall, or even if you've been told something else in this case, or in this, well, let's say in this case. Yeah, because of course, you can define the singleton pi in parameters by x equals z1 and use, yeah, I mean, I want to use pi for all examples from now on. So you put z1 equal to pi. So by an interval, we mean a set x, sorry, set, let's say I, subset I of the R, such that if x is less than y is less than z, with x and z both in I, then also y belongs to I. Okay.
But in that case, the reals also include the infinity and minus infinity. These points.
No, the reals don't need to include minus. The reals definitely do not include minus infinity and plus infinity as points. This is a correct definition of interval. It includes this as an interval, but it doesn't include minus infinity. But still, this set enjoys that property. If you've got any three elements in a chain where two of them are in the interval, then the middle one must also be in the interval. So, I mean, this is definitely correct. Oh, and I once again forgot to move the camera. Never mind, it's going to be a poor quality video this week. So this is, I mean, it may not seem very much, this result, but actually this kind of result has turned out to be really important. So this property here that's established by this theorem has a name. So this says that the theory of rational linear expressions is what's called o-minimal. And it turns out that lots of even much more powerful theories than rational linear expressions are also o-minimal. And that fact that they're o-minimal, it doesn't look like a very exciting property, but it turns out to be massively useful for understanding a lot of things. In particular, any o-minimal theory has something allows some operation called cylindric decomposition of definable sets, and that turns out to be really mathematically useful. So I just want to give you here some mathematical context for this, without going into details, because actually I don't know the details anyway. So o-minimality is a really important, I'll just say an important contemporary topic in mathematics. Topic in mathematical logic. Goes back to the end of, I mean, it goes back like 30 years or so, but it's been so rich that it's still the study of o-minimality is really still ongoing and very fruitful in mathematical logic. And a really important result is the following strong generalization of this theory, of this theorem here, the o-minimality of rational linear expressions. So there's something called Wilke's theorem. And that's that if we consider the theory over the reals of, well, what we've got, so 0 with addition, 1 with, we're going to throw multiplication in now. So this is now the theory of real closed fields, Tarski's theory that's decidable. So that's also the decidability of that is proved by quantifier elimination techniques. And again, the quantifier elimination techniques establish o-minimality. You don't need to stop there. You can also add the exponential function. So the function, this is the exponential function e to the x. And then you get a really, really powerful theory, mathematical theory. And this is o-minimal. The Wilke's theorem is that is o-minimal. And again, well, you might say, so what? Well, so any set definable in parameters is a finite union of intervals, because as I said, that statement allows something called cylindric decomposition. And using that, so then using this result, several open results in number theory were resolved as a consequence of this. Well, I say several, some open, I mean, they gave some new, very new powerful machinery for, by number theory, I kind of mean the number theory of real numbers and what of algebraic parts of analysis in some sense. Anyway, there's a beautiful subject here that's been developed, and essentially it's all based on derived from quantifier elimination. And in this case, again, the o-minimality is again established by proving a quantifier elimination result. The interesting thing in this case is it's an open question if this theory is decidable. So if we don't have the exponential function, it's known to be decidable. In the case that we do have the exponential function, then one gets into lots of really tricky questions about whether functions involving exponentiation have rational results or not. And that's very difficult to answer. It's like, you might know there's an open question, is e plus pi a rational number or something like, or something like that. There's similar kinds of things to this. And there's a very important conjecture in number theory called Chenuel's conjecture, which is about somehow the independence of the exponential function from rationality, from the rational numbers. And if Chenuel's conjecture is true, then this theory is decidable. Anyway, so those are some connections. So this was the second, this theorem, the o-minimality, that was the second application of quantifier elimination for rational linear expressions. The third one is not going to spend very long on, because I did promise you an early finish, and well, anyway, we're still early. The second one is to do with comparing the theory we've got, comparing the reals and the rational numbers. So I've been looking at this theory of rational linear expressions over the real numbers, but obviously the theory makes sense, all the operations make sense for rational numbers. We've got addition and multiplication, 0 and 1, and we've got multiplication by a rational constant. So all that makes sense also over the structure of rational numbers. But is there a difference? So to begin with, let's consider the signature where we do have multiplication, so 0 and plus 1 and times over the real numbers where we started with in this lecture, Task's theorem, and also over Q. Can we find a sentence that distinguishes between these structures here? Can we find a sentence over this that's true in the real numbers? Well, that's true in one of the real numbers or the rational numbers and not true in the other. Any idea? Can anyone see it straight away? Right, very good. Yeah, so the existence of a number whose square is 2. So there exists x times x equals 1 plus 1. Distinguishes between these two because obviously that's true in R, but it's not true in the rational numbers. So this distinguishes between the rationals and the reals. The question is there any way of distinguishing between the rationals and the reals without using the full power of multiplication? Can we do it? We've got quantification, and can we do it in the theory of rational linear expressions, in which we have everything except the multiplication, but we've also got the linear order, and we've also got the multiplication by a rational. And the answer is no. So from the perspective of theory, of the logical theory, over that signature, you cannot tell the difference between the rationals and the reals. Moreover, it's not just a question of a sentence is true in one structure if and only if it's true in another. We have a stronger property that ties those two structures together. So consider the embedding, which I'll call iota, which embeds the rational numbers in the reals. So iota of Q is Q. But the theorem is going to say this signature, the theory, the signature, or the signature for any formula A, let's write its three variables, x1 through to xn, in the signature of rational linear expressions. And any environment in rational numbers, so an environment is function rho from variables to now rational numbers. The formula A is true under the environment rho if and only if in the real numbers A is also true. Well, again, under the environment rho, if you like, but a more formal way of writing it would be under the environment that we get by composing iota with rho, because here we've got the environment returning rational numbers, and here we want to return real numbers, and I'm being a little bit fussy by saying, well, we're doing that using the inclusion function that takes us from rational numbers to real numbers. But this implies in the special case that any sentence is true in the rational numbers if and only if it's true in the reals, because then we don't have any variables to interpret. But more generally, even formulas and variables, as long as we instantiate the free variables with rationals, They're going to be true in the rational numbers if and only if they're true in the reals. This is not a trivial property. You may think, well, that's obviously the case. We've got more reals than rationals, so, you know, obviously that's going to be true. But it's not true. It's not trivially true at all, because in this case, our quantifiers are ranging over rationals, and here they're ranging over reals. So here, if we've got a quantifier, we say for all x, we mean for all rational numbers x, whereas here we're saying the property holds for all real numbers x. And it's not at all trivial that those quantifiers agree. Okay? So there is depth to this result. And moreover, it gives us an example of something we're going to meet later on in the course. In other words, I'll just state the terminology now, but this is something we'll meet later on in the course. The function iota from rationals to the reals is what's called an elementary embedding. So this property is exactly the property that defines an elementary embedding. So as I say, that's something for later in the course. I just want to say a few words about how to prove this. But as you can see, I'm not going to say much because I've put it down at the bottom of the board here and there isn't very much space. So how do we prove it? Well, this is obviously true for quantifier-free formulas. So let's have another star. So star obviously holds for quantifier-free Q.F formulas. For a non-quantifier-free formula, for arbitrary A, we have over the reals, what we established today, we did our quantifier elimination result. So we have A, if and only if, well, for all x1 to xn, A holds if and only if it's quantifier elimination, A quantifier free holds. And we did that because we established quantifier elimination over the reals. But all steps of the quantifier elimination that we did, you need to check for yourself that all the steps that we did, they're all valid over the structure Q, over the rationals. But by inspecting the proof, sorry, my writing's getting very ugly, but by inspecting the proof of quantifier elimination, and we read that full down, but by inspecting the proof of quantifier elimination, also we have that for the same quantifier-free formula, all the steps of quantifier elimination go through. So for the same quantifier-free formula, over the rationals, A is equivalent to the same quantifier-free formula. So then by the chain of reasoning, so for any formula A over the rationals, it's equivalent to this quantifier-free formula, which has the same interpretation automatically in the reals, which is equivalent to the same A. And that is how one establishes that result. Right, okay, good. That's everything for today. I did promise, so we do have a slightly early finish. I'm going to stop the recording.